Okay, let's get started. How many of you have already bought the book? Which edition did you get? 8. Okay. As I said, if you are seriously interested, 9th edition is better. They finally gave me access to online access. I don't like reading a book on a screen. It's very hard to do. But I looked through it. They have made significant changes. For your information, they deleted the chapter on nuclear rocket propulsion. So in that sense, the 9th edition is not better than the 8th one. But they have references to new launch vehicles and stuff like that. That's would be useful. Okay, so if you are really interested, I think you should try to. Those of you who haven't bought it yet, try to get the 9th edition. Okay, we'll cover nuclear propulsion in my notes. I think that should be more than enough. Okay, now homework problem. Some of you are under the impression that I'm asking you to do a lot of stuff before I have even taught you about those things. That's not true. All I'm asking you to do is just collect the necessary data to do the analysis later. Okay? So if we go to, for example, the example I gave you, I just want to read it. I don't want to run it. Okay. Great. Okay. This is the code that extracts the performance for SpaceX Falcon 9 version 1.1, an earlier version. Okay, they have a newer version 1.2, FT, and so on. The data, for example, I wanted you to collect some of these. As long as you are collecting the data, you might as well collect the entire data. Height, diameter, what is the launch pad mass? That's very critical. Okay. How many stages does it have? Does it have any boosters? Now, Falcon 9 is a serial stage vehicle, meaning that the first stage operates, is discarded, second stage operates, discarded, so on. On the other hand, a parallel stage vehicle, like, for example, the space shuttle, the main engines as well as boosters work at the same time, are ignited at the same time. But as it goes up, the boosters finish their work, are expended, jettisoned, while the main engine continues to work. So that's called parallel staging. Once again, it was the Russians that came up with that, or at least were the first ones to use that concept in their very first ICBM. I forget the number. Anyway, the very first ICBM they made. Now, this is a serial stage vehicle, so it has only 2 stages. Then the question is, in this case, what is its capability? How much mass can it launch to LEO, low Earth orbit? Okay, low Earth orbit, for our purposes, around 150 to 200 kilometers. Okay, low Earth orbit is anywhere from 100 kilometer altitude to something like 1,000 kilometers. Okay, but for this purpose, when they usually quote that, it's typically around 200 kilometers or so. Mass to GTO. Now GTO means geosynchronous transfer orbit. Okay. Now there are different types of orbits. Low Earth orbit is just low orbit. Now geostationary orbit is an equatorial orbit, perfectly circular equatorial orbit of a certain height that matches the satellite speed with the rotational speed of the Earth, so that the satellite remains stationary over a particular region. Okay, three geostationary satellites will provide complete coverage. Okay, the poles are a bit lacking. That's why our surveillance satellites, in the military surveillance satellites, use not only the geostationary satellite but also polar orbiting satellites, so they can cover the poles as well. Okay, because missiles could be launched across the polar region, that sort of thing. Anyway, GTO is not geostationary orbit. It is stationary transfer orbit. Okay, the launcher does not launch your satellite into geosynchronous orbit. He essentially launches it into a highly elliptical orbit with the perigee about 200 kilometers or so, but the apogee such that the height is equal to the height of a geosynchronous orbit. Okay, that's all it does. Then it is up to the spacecraft, owner to provide the engine on board the spacecraft to not only circularize the orbit, so it becomes a circular orbit, is a highly elliptical orbit, but also change the plane from whatever plane it was launched into to equatorial plane. Okay, so you always see capabilities quoted in terms of LEO, in terms of GTO, and in terms of SSO, Sun Synchronous Orbit. In some cases, you want to be on the same location every time for satellites that use visible spectrum to look at things. So this is a Sun Synchronous Orbit, which is actually slightly retrograde orbit. Okay, prograde, retrograde. Prograde means the satellite rotates in the same direction as the Earth, and retrograde is more than 100 degrees, that sort of thing. So anyway, first stage. First stage does most of the work of taking the spacecraft up to a few tens of kilometers. Depends on the design. So once again, the various things you need to know is masses are extremely important. What is the inert mass? Meaning structure, engines, that sort of thing. So essentially think of it as useless mass. It would be nice to build a rocket vehicle with zero inert mass, but it's not possible, hypothetically. So you have to have some mass. But the whole idea design is to minimize that as much as possible. It tries to squeeze out as much mass as possible out of the inert mass, yet retain reliability. Okay? Not at the cost of reliability. So propellant mass, as you can see, rocket vehicle is mostly propellant. Okay? Huge amount of propellant. So you need to know these things. And then what kind of propellant does it use? In this case, RP1, kerosene, oxidizer liquid oxygen, and other sort of considerations like propulsion. In this case, I will talk about the design philosophy. SpaceX designed to go with building a small engine, which is easier than building a very high thrust engine, and then just use many of them. Okay. In this case, 9 of them. There was a Falcon 1. I don't know if you remember Falcon 1. Falcon 1 just tested a single engine, okay, a vehicle with a single engine. Had many failures. They had to work hard to get all these things going properly. Now you have Falcon 9 with 9 Merlin 1D engines. The earlier version was Merlin 1C. Things like what is the engine type, gas generator, and things. I will come back to that at some point. Turbo pumps are used, obviously, for first stage. You need a huge mass flow rate of propellant, so only way to provide it is using a turbo pump. Okay. Most important characteristic, what is the thrust of the engine? Merlin, as you can see, 1D generates about 654 kilonewtons of thrust at sea level. Thrust in vacuum is always higher, okay, by a few couple of tens of percent, so to say, 10 to 20% or so. Now, specific impulse. Specific impulse essentially is how good the engine is. Okay? In rocketry, we want to generate as much thrust as possible per unit mass flow rate of propellant, because the propellant mass is what we want to minimize. So the higher the specific impulse, the better. So definition is the thrust divided by the mass flow rate, normalized by using G naught. Okay? That is gravitational acceleration. Its value, of course, is 9.81 meter per second square, and the value used corresponds to the G value at the surface of Earth. Okay? Now, that specific impulse definition doesn't change if you go to Mars. Okay? G naught is still 9.81. It is just a way of making the units of specific impulse seconds, no matter which system you use, British or metric. Okay? And then the impulse is seldom quoted. It can be computed. Usually the burn time is specified. Okay, how long the engines burn. Okay, you have to design the engines for a specified burn time. Okay, and usually the testing, when you do the testing, you try to run the engine for longer than it is expected to operate, just for just to make sure it will work. So the impulse is essentially the integrated thrust. Okay, so those are the two definitions that you should remember. Okay, specific impulse, always less at sea level compared to vacuum, the same engine. We'll see the reason why later. Okay, so when you mention thrust or the specific impulse, you must tell me whether it's vacuum or sea level. When that qualifier is omitted, it usually means vacuum. Okay, but sometimes it's not clear, so you have to be sure what value it is. Dry mass of the engine, that is of interest, because as engineers, we want to build an engine with as high a thrust weight ratio as possible. Okay, this is the thrust of the engine divided by the weight of the engine, which is mass of the engine times G naught. Okay, please don't make the mistake in this class of confusing between weight and mass. Okay, that's very, very important. Okay, this is mass. The dry mass is 450 kilograms, but when you compute the thrust, you have to multiply it by G naught to get the weight. And the thrust weight ratio, higher the better, because that is a good engine. Right now, Merlin 1D, I think, has the highest thrust weight ratio. It beat the NK-33, the Russian engine, which had a thrust weight ratio of 137. Okay, that's an achievement, really. Anyway, other things like, what is the chamber pressure of the engine? This is an important quantity, as we will see. What is the expansion ratio? Now, the expansion ratio is usually denoted as epsilon. It is the exhaust area divided by the throat area. Okay, the expansion ratio is 10, 12 for engines that operate in the atmosphere. For vacuum engines, it can be as high as 300. Okay, so when you look at the vacuum engine and the one that operates through the atmosphere, you will see the expansion ratios, change quite a bit. Yeah.
The exhaust, the area at the end of the engine bell, or at the nozzle?
The nozzle. Well, the nozzle exit area. The nozzle is a convergent divergent nozzle, and it is this area here. And this is the throat area. Okay. Restart capability, throttling capability, these are issues that get into the engine design, whether the Engines can be gimbaled. That is important because you have to have some way to control the thrust vector. Okay. Typically in the West, we usually build the engines so they can be gimbaled over a few degrees. Yeah, 5, 6 degrees, something like that. Throttling capability is important because as the vehicle goes through what is known as the max Q. My apologies. How many of you know what Q is? What? Okay. Q is the dynamic pressure. Okay. Q is half the density times the velocity square, or it can also be written as half the pressure times square of the Mach number. This is aerodynamics 101. You should know that. Okay. Now, initially, as the vehicle lifts off, the density is high. Yes, density is sea level. The velocity is 0, obviously. So Q is 0. But as it goes up, the velocity goes up, but the density comes down. Okay. So Q, if you plot versus time, it is 0, and then it reaches a maximum before it comes down. That's called Q maximum. Q max. Now, that is the point in time where the aerodynamic loads on the vehicle are the highest. So it is useful to throttle the engine down as you're going through Qmax point. Okay, that is usually when you watch a launch, you say Qmax and so on. Also, even satellites, non-human flights, just carrying satellites, these are sensitive instruments. So you don't want to subject them to very high gravitational loads. Typically, the limit is about 5G. So as the vehicle goes up, the thrust is the same, roughly, but the mass of the vehicle is coming down rapidly, and therefore the G forces exerted keeps going up. So at some point, when it reaches, say, 5, you need to throttle down the engine, reduce the thrust, so that you don't subject your payload to high accelerations. Yeah?
So for the dynamic pressure, I think you need a gamma over 2 P Mach.
Oh, thank you. Looks like I don't remember my own aerodynamics 101. Okay, that's gamma, should be there. Anyway, so some of these things, interesting, compile them, okay? Then, of course, the second stage, similar things, okay? Nothing special there. Second stage usually operate in vacuum, so vacuum specific impulse is important. Then what it carries, in this case, Dragon specifications. Falcon 9 is used for launching cargo to the International Space Station, so it is carried in the Dragon spacecraft. So it's not an inert thing. You had to have a power source. So in other words, you had to have solar panels to provide the power, or batteries, as the case may be. In this case, solar panels. You have to have propellants on board, so you can maneuver the spacecraft to the International Space Station and also come back. You have to execute a delta V to deorbit and things like that. So what kind of propellants they use? In this case, obviously, in space, if you're going to stay there for a long time, the propellants must be storable. Okay. There does exist technology to store cryogenic propellants in space, but I don't think it is well tested. So invariably, one uses something like hydrazine nitrogen tetroxide, and I will talk about a case in which they used RP4 and hydrogen peroxide. You know, the Air Force flies a really hush-hush, top-secret space shuttle-like vehicle, X-37, that is launched on an Atlas V, goes into orbit, stays there for 600 days, 300 to 600 days, doing who knows what it does. It's classified, highly classified. But the propellant used obviously has to be storable. And in this case, I think they chose a non-toxic combination, which is JP4 and not RP4, JP4 jet fuel, kerosene essentially, highly refined kerosene in various forms. And hydrogen peroxide. Okay, that's the only engine I know that is a hydrogen peroxide engine. So anyway, how much propellant does it carry, or how much power? You had to provide power, so you had to have several panels, things like that. Okay. Part of it is pressurized, part of it is unpressurized. There is some cargo you have to carry in pressurized volume. Others you can carry, like fuel, for example, in unpressurized bay. Now, stages are connected, okay, structurally. That interstage, you need to know how much the interstage mass is, because usually when you jettison the previous stage, you also jettison the interstage. Okay, and then payloads are always protected by a payload fairing. Okay, in fact, the diameter and length of the payload fairing determines what you can carry. Okay, the size is also important in space. Okay. The largest diameter fairing so far is about 5.2 meters, I think on Atlas V. But that 5.2 meters is enough to carry the space plane, X-37. Okay. The SLS, NASA SLS vehicle that's being designed will have a payload fairing of 10 meters. Imagine 10 meters, 30 plus feet. Now that would be needed, of course, to carry whatever modules to build an international, space, lunar village or whatever. Okay. So, but you have to know what is the payload fairing mass. Okay. Oh, this one also has 5.2 meters. Yeah. And then the engines. Okay. Merlin 1D, what is its thrust? What is specific force? What is its mass? What is the expansion ratio, burn time, mass flow rate, throat area, and so on. You can see the vacuum version provides higher thrust, but essentially this engine adapted with a longer nozzle with a higher expansion ratio. That's all. This expansion ratio is 100. This one is 16. So they essentially fit a nozzle expansion and make it a vacuum engine. Okay. Other interesting things, if you can collect. Anyway, yeah.
What are DE and DT in those lists?
Oh, there's a diameter. Diameter, the exhaust diameter, throat diameter. Okay. Any questions on this? That's all I'm asking you to do. Okay. And in the first homework, I'm asking you to calculate the overall thrust to weight ratio of the launch vehicle on the launch pad. Obviously, that has to be at liftoff, I should say, at liftoff. So obviously, that has to be greater than 1 for the vehicle to lift off. Okay. Typically, it is about anywhere between 1.25 and 1.5. Now, you can't have it too high because it requires higher thrust, which means more powerful turbopumps. On the other hand, you can't have it too low because it will then take forever to clear the launch pad and accelerate towards the target. Missiles, on the other hand, have a very high thrust-to-weight ratio because they have to get going to the targets, pretty fast. Okay, that is one. And also compute the thrust-to-weight ratio for your engines. Okay. Now, that should be anywhere between, for the engines, it should be anywhere between, say, 50 and 140, something like that.
You said.
Okay.
You said for the stages.
For the engine.
Okay, for
For the engine. A stage may have many engines, so I just want the engine. So I want you to know what the engine looks like, what it's capable of doing, what is the launch vehicle looks like, what its capability, so on. Okay? So that is all I want you to do. In other words, that the green portion of that SpaceX.m is what I would like you to gather. And then we'll use that in the future. I don't know how to do this. This is all random, so you just put your hand, pick one. It doesn't matter who goes first, who goes last. It's, just pass it around, please, and give me back the remainder. Okay, so when you know your launch vehicle, go to Spaceflight 101, gather the data, but just don't rely on the Spaceflight 101. Usually their data is accurate. Okay, I have looked at them quite a bit, but also look at other sources. For example, the manufacturer of the vehicle. Wikipedia, for example, sometimes, Wikipedia, you have to be careful. Sometimes the data can be corrupt. But whatever data you use, as engineers, we need to run them through a sanity check. Does this make sense? If the thrust-to-weight ratio of a launch vehicle becomes less than 1, obviously there's something wrong with the data. Things like that. Okay? So apply a sanity check to your data. Okay? That's pretty much all that is about the homework. All right. Any questions for me on that? Yes?
Do you want us to submit it in a Word document or as a .m file?
Ah, okay. All right. I usually require that the homeworks be in the form of a report. Okay, some of the homeworks may require you to run a MATLAB code, but just don't submit the MATLAB code, please. Okay, so you can append the MATLAB code if you like, but you must submit a proper report-like thing and highlight the answers. Okay, very important. When you're grading many things, you don't want to read through to find out where the answer is. Okay, highlight the answers. Okay, and please follow the convention, your last name, and then the homework number, .pdf or .docx is better. Okay, if you handwrite something, scan it, convert it into a PDF, a single document, and submit. That's okay. Yeah.
I'm sorry, I got excited when I read. You said you wanted it as a Word document?
Word document or PDF. Yeah, Word is better. But some of us who like writing, well, if you write it, convert it to a PDF. Okay. But do highlight the answers, please, so that we don't have to search through. For this one, just submit your, that portion of the green portion of the MATLAB code. That's all.
For this homework, we're just submitting that, but for this homework, we're submitting for answers.
What I said covers all homeworks. But for this homework, obviously you're just going to collect the MATLAB code, right? Comment out the data, okay? And right in there, you can just write what the thrust-weight ratio was and submit it. Okay, that should be adequate.
For this homework, it would just be okay to turn that MATLAB file, or you want the original still.
MATLAB is okay for this one, okay. But do, indicate what the thrust weight ratio is. I don't know to search through to find out what it is. Okay. But that is another thing that I forgot to mention. Okay. Midterm is usually a take-home exam. Essentially, I think the analysis of the vehicle you have, collected the data for. But I always like my students to report back in an AWA format, okay? Because that will help you in your future career, because you will be submitting reports, making presentations at AWA and so on. How many of you are AWA members? Oh, if you're not, please. If you're going to be an aerospace engineer, you have to be a member of AWA. Come on. For students, the annual fee is very small. Okay, we purposefully keep it low, and that helps. If, for example, if it is an AWA book you're going to buy for whatever reason, you get a huge discount that more than compensates for your annual membership. So things like that. When you go and present a talk at a conference, if you're a member, you get a lower registration fee and so on. So the membership fee is easily covered by one of those privileges. So if you're not, please become a member. It's useful. As I was saying, AWA format is what I like your reports to be in. I will put a sample on D2L, and also I will provide a sample final report. And for the final exam, we don't usually have a final exam, we have a final project report, right? So for that, you need to produce a 10 to 12 page AWA format report, paper, preferably paper, and a PPT, because you are required to get up and present your findings to your peers in the class. Okay, so something like a 5 to 8 minute presentation. So those are the two deliverables for the finals. Okay, any questions? Yeah.
Can that be like one report for the whole group?
Yes, yes. If you work in a group, it is one report. Okay, all right. What else do I want to say? Okay, so that is that on the homework. So if you have any questions, just let me know. Don't feel shy. How many of you logged on to D2L, looked at the stuff I put under useful module? What is the excuse for the others who did not? Okay, please do look. You have Apollo by numbers, okay, that has a nice summary of all the Apollo flights, 1 to 17, not even the flight, 1 to 17. 17 was the last one, okay, and has all sorts of statistics, numbers galore. I mean, engineers, we love numbers, all sorts of things. So masses and times, and so for those of you who would like to choose International Lunar Village for your final project, that's a good start to see what they did and what needs to be done. Okay? Until Obama came into the office, presidential office, and canceled the Bush program, Constellation program, NASA was very hard at work on getting the astronauts back to the moon by 2020. Believe it or not, 3 more years we would have been there. Okay, but President Obama chose to cancel the program, but they did a lot of work. So if you go to NASA and type in lunar exploration, you will get there's a varieties of things, including a report. Okay, I also found this under that program. They also prepared this NASA SP, which is the Mars portion, because essentially Bush said, go to moon as a stepping stone to Mars. So NASA worked not only on the lunar exploration program, but also how to extend it to Mars. And that report I put on D2L, that NASA SP. This is a more special report. I forget what that SP is. Too many acronyms. Talks about Mars. Okay, the habitat, transportation, how to get there. All those things you have to work out. If you're going to do something like that. I also put a recent, I think July 2016 database by Union of Concerned Scientists on the satellites in orbit around the Earth at that time. Now it is interesting to see because you can see the satellite, all its characteristics, the orbits and whatnot, the dry mass, the launch mass, and all that, along with what vehicle launched that into what orbit. Okay, so it's an interesting thing, to look through. Now, how many of you looked at unit conversion? Okay, it's a nice spreadsheet prepared by none other than the gentleman sitting in the back who used to be my TA for ASEN 4013 with my help. But you just plug in whatever number, 10,000 pounds of thrust, you get it in newtons without a mistake. Okay. On the other hand, if you try to use a calculator, you can make a mistake. Okay. So it is, easy to go back and forth between metric and British systems. I hate the British system, but we are stuck with it in this country for the foreseeable future. So we had to use it because all the specifications are used in pounds and this and that. So, but it's better to always work in metric units. The chance of you making an error in metric units are slimmer. Not zero, but slimmer than if you use a British system. Did you hear the story? We lost a Mars mission, a spacecraft, because the engineers provided the thrust in British units or something like that, and slugs or something like that, and they programmed it wrong. Mission is down. Hundreds of millions of dollars lost. So, metric units, you won't make a mistake. Our chances are less. Okay, what else? Also, compile this rocket engines. Okay, starting with the very most powerful engine ever built, 6.6 meganewtons of thrust, RP1, cryogenic, the hydrocarbon engine, followed by J2, which was the very first cryogenic engine we ever built. Look at the thrust levels. Okay, and we go through the whole thing. United States, Russia, Europe, China, India, and so on. Okay, so a nice table to tell you what the characteristics are. If you find any error, please let me know. It's very difficult to get accurate data and so on. So we always have to check and check and check. Any questions before I carry on? The news of today, Atlas V launched a missile warning system, a satellite, successfully. Zero failure so far for ULA. They're doing very, very well. Okay, reliability is oftentimes more important than the cost in this business. Because imagine a $1.5 billion satellite sitting on top of your launch vehicle. And if you try to squeeze $50 million out of launch cost and lose $1.5 billion satellite, that doesn't do well, does it? Okay, so reliability is oftentimes important. Is more important in this business more often than cost than anything else. Okay, and given the thousands of parts in a typical launch vehicle, all those parts have to work as designed, as specified, for the launch to be successful. Okay. All right. Then, Japan is going to launch their H-2A launch vehicle. Who has H-2A? Oh, it's still probably there. Okay. Who has H-2B? Okay. Anyway, they're launching their H-2A on some secret mission once again. You know, all nations now want to have satellite surveillance or whatever. Falcon 9 is going to be launched once again from Cape Canaveral. The last launch was from Vandenberg on the west coast. Now they are ready to launch sometime in February. So they did get back into the game fairly quickly. I must hand it to Elon Musk. He knows what he's doing. Pardon me?
That one's going to be a reused state as well.
Say it again?
It's the reused booster. They're reusing one of the boosters they've recovered.
I don't think so.
I know it's coming up soon.
Are they?
Coming up soon, yeah, with that European satellite company.
Not with the February launch, is it?
Originally, it was supposed to be for December, and then the accident happened, so they pushed it back a couple months.
Okay, that's another thing that was pointed out in the press. They have recovered, I think, five first stages so far, but nobody knows whether they have been able to refurbish and test and make sure that it will work so they can be used for the next launch. I don't think this upcoming launch is the one. I could be wrong, but I don't think so.
They've got contracts. I think it's SES. I think that's the European country. They've already got contracts for it.
SES-10.
Well, we'll see. Okay, it's one thing to recover the first stage, but it is a totally another thing to make sure that is refurbished, examined, repaired if necessary, and launched. One of the reasons space shuttle became so expensive. Now, originally it was thought that space shuttle, hey, we can get it back within a week, we can send it back again. They were planning as many as 50 launches with three shuttles, okay, that sort of thing. That would have brought down the cost significantly. But turns out, since it is a manned launch vehicle, making sure that the next launch would be successful would require a huge amount of work. The engines had to be dismantled, tested, put back, paperwork, stacked that high had to be filled before it went back up again. And that was made the cost of a special launch $500 million. Okay, so
Part of the reason their safety margin would be so high is because they didn't have any launch escape system. Their plan was just grab a parachute and jump out the door.
talk about building in failure points into your design. You
Right.
put the space shuttle on the side of a tank containing, propellants, and those propellants are very low temperature, so ice forms on that. And naturally, the ice chunk can detach and hit your vehicle. Okay, would have been better to put it on top somehow. Okay, another, no escape system. So they had to make sure that the vehicle was absolutely very close to 100% safe. Whereas the conventional launch systems have a launch abort system. So if something goes wrong on the launch pad or during the initial flight, you can just jettison and land back on a parachute. Okay, so some of these things, decisions you make in the beginning come back to haunt you. Okay, because it's very difficult to change the design once you build these things into it. So what makes rocket engineers and rocket scientists special is that we always say, what if, what if, what if, and think of all possible failure modes and try to mitigate them as well and as inexpensively as possible. Obviously, you can build something extremely safe but extremely expensive so that nobody can use it. But okay, all right. As I said, I talk a little bit too much, but I guess that's what I'm supposed to do. All right. Come on. All right. All right. The two billionaires that are competing with each other, Jeff Bezos and Elon Musk. Of course, Jeff Bezos has this Blue Origin vehicle. Where's the orbital sciences? Blue Origin vehicle, it's a suborbital launch vehicle, and they have recovered it successfully many, many times. Okay. Now, one of the things, once again, when you program the stage to come back, you can make it follow a very rigid set of rules. Okay. But they discovered that you had to have some margin, a fuzzy type of algorithm, so that it did not put too much stress on the engines and structure and so on. So they used a fuzzy logic to, but still accomplish the task. So you allow for margins. This is, of course, the first stage recovered by SpaceX in December, and this one is the new Shepard. That's what Jeff Bezos calls it, Shepard, for the first person to fly in space, first American astronaut to fly in space, Shepard. Isn't that beautiful? I could watch it, many times. It's a real accomplishment. Okay, but you can talk about recovery in the first stage, but you have to also think about what you're trying to accomplish. Okay, the engines are the most valuable part of any stage. Okay, the rest of it is not that useful. Okay, so you want to bring back the engine, but how do you bring it back through the atmosphere? Whether you use rocket thrust to slow it down through the atmosphere, in which case you have to use propellant, which means your payload capacity goes down, or the main vehicle. Okay. On the other hand, ULA is thinking of recovering only the engines of the first stage. So they are attached to the first stage, but they can be explosively detached. Okay, and then the engines re-enter using a heat shield. In other words, you're letting the atmosphere do the work of slowing down the engines. And then you don't want the engines to splash into the ocean, okay? Because salt water gets everywhere, and how do you refurbish it? Okay, so they essentially want to use a helicopter to catch it and then bring it back to wherever they want to bring it back. That is a little smarter way of doing things. The SpaceX way of doing things actually introduces a penalty of something like 10 to 20% on the payload capacity, because you had to reserve fuel in the first stage to bring back the first stage using rocket thrust. Okay. Now, Blue Origin has ambitious plans. Okay. Now, their ambition is to build this vehicle called New Glenn, for Scott Glenn, and then their next vehicle is going to be a New Armstrong. Okay, I appreciate Bezos for giving credit to these heroes of our space program. Anyway, look at the size of this compared to Saturn V. Saturn V is the biggest vehicle we ever built, right? N1, the Russian N1 was slightly bigger, but it did not work, remember? So this was a successful one. Compare that to the various launch vehicles we have. This is Antares. Who has Antares? Okay, all right. The Antares 100 and 200. The difference is Antares 100 used the Aerojet version of the NK-33, which we'll talk about in a minute, Russian engine. Now, after the disaster launchpad explosion, they essentially said, to heck with that engine, we're going to use the RD-181. So that is the 200. So I would like to see what the difference in the two versions are. Obviously, different thrust, so they had to accommodate all that. And anyway, Antares, Soyuz, This has, I don't know, 1,500 launches or something like that. I forget the exact number. Highly successful vehicle. They make launching routine. Apparently, you supply the payload, they go through a 2-week, they put it on the vehicle, prepare the vehicle, put it on the vehicle, fly it, done. So, it's become very routine. This is a very reliable launch vehicle. There have been some failures recently because they tried to use a new upper stage or something like that. But those sort of things, have to be expected because, it's something new. Ariane 5, the European one, heavy launch vehicle, parallel staged. This is also parallel staged. You see these, 4 cone-shaped things. Those are the boosters that are discarded. Okay, so this is actually a modified version of the first ICBM they built to launch hydrogen bombs, capable of launching hydrogen bombs towards us. But anyway, parallel stage, 2 solid rocket boosters, main engine cryogenic. Okay. The upper stage cryogenic. They used to use hypergolic one, but then they replaced it with the cryogenic one. And they are going to build Ariane 6. And interestingly, the way things go, they want to make Ariane 6 a solid propellant all stages. Why would they do that? Solid propellants have a lower performance, specific impulse, something like 270 seconds at sea level, whereas the cryogenic engine has 430 seconds sea level. Why would one want to do that? Any idea? Yes. Oftentimes, the simplest and the simplest turns out to be cheapest, because when you talk about launch vehicle in space, the more complexity you build in, the higher the costs are, and even though you get higher performance, so what? So they're going to go back to solid rocket vehicles. Atlas V, our workhorse, Yola workhorse, launches most of our DoD satellites, as well as some civilian ones. Okay, it just launched our missile warning system satellite. It can have a 5.2 meter fairing, so it can even launch our X-37. Okay, this is cheaper than the Delta IV Heavy that ULA also launches. But this Delta IV Heavy is necessary for heavy payloads. Okay, so that is why they keep it going. There are certain payloads that cannot be launched by Atlas V, even with 5 solid rocket boosters. Okay, Atlas 551. Who has 551? Atlas 551. Okay, Atlas 551 means 5 boosters, 5-meter fairing, and a single upper stage engine. That's what that means. Okay. The simplest version, of course, is Atlas 401. Okay, that is just no boosters. Okay. Welcome. This is what ULA is designing now. They are hiring a lot of people to do this. Okay. This is supposed to replace both the Atlas and the Delta IV Heavy. Delta IV Heavy is nice, but expensive, in excess of $300 million per launch. Okay. That's a lot of money. Okay. So they want to get rid of these 2. This one, simply because the Congress said you can't use the Russian engine anymore to launch DoD government payloads. A lot of this business is government payloads. So if they have to get rid of RD-180, the Russian engine, well, they might as well design a new vehicle, and that's what they're doing. And Blue Origin and ULA have gotten together. They are going to use the methane engine B4 being developed by Blue Origin. Okay. Why methane? Well, once again, a legacy of our Mars stuff, because supposedly methane is easily available on are easily manufactured on Mars, and therefore methane engine would be great. Now, it has other advantages. It's a clean burning fuel compared to kerosene. So that's a significant advantage. So if you're going to have a reusable first stage, a clean burning fuel would be a great advantage. So that's another reason they're going to go and use the Jeff Bezos BE4 engine for the first stage. And then they have their own modified Oral 10. Oral 10, Pratt & Whitney engine, upper stage engine, has been a highly reliable upper stage engine. But it is pretty old. So there are ways to improve the manufacturing process and things like that and make it more versatile. That's what they're going to do. Falcon 9 we talked about. The beauty of this is one small engine, less than a meganewton thrust, cluster them for the first stage, use the same engine for the second stage, but the vacuum version, we're done. Now you take the basic cores and put 3 of them together. You have a Falcon 9 Heavy with a capability of launching 50 metric tons into low Earth orbit. That's a lot. Space Shuttle was only 32 metric tons to low Earth orbit. And it was necessary to use the Space Shuttle to build the International Space Station because only a Space Shuttle could carry the heavy modules. Okay. Now, 50 metric tons would go a long way. That 50 metric tons can actually be, this capability can be used for the International Lunar Village because it can transport significant payload to the polar regions of the moon. New Glenn, this is still a gleam in Jeff Bezos' eyes, but he wants to build it, and when it is built, look at the first stage. It's taller than the first and second, first stage of the Saturn V. Uses 4 B4 engines, I believe, and has a huge payload capability. Okay. Trademark is this feather. Do you know why? Why the feather on those things? It looks nice, though. Okay. Let's come to NASA. Okay. NASA was originally building essentially this one. Okay. It was called Ares 5 before the program was canceled. Then there was an Ares 1 to carry the human beings. Okay. This is cargo vehicle, the human vehicle, so to say. It used a single space shuttle solid rocket booster with the second stage on top, and that was supposed to be the crew launch vehicle, Ares 1. They built it, but it had some problems. For example, very high thrust fluctuations, which would, of course, harm the astronauts. Okay, so they were trying to solve the problem, but then Obama came in and canceled the whole Constellation program. Okay. Now, the Senate, the Congress, essentially, they lost a lot of jobs in their constituencies, so they had to do something, right? So they reinstituted the program and asked NASA to build this heavy launch vehicle. Okay. So that's what is being built now. Okay. Now, that's why it's often called Senate Launch System. It's a space launch system. But anyway, that's, the political system. Anyway, the initial one is going to be 70 metric tons to orbit, 5-segment solid rocket boosters. The 4-segment one used on the space shuttle is modified. The whole philosophy was to use as much of the space shuttle gear as possible. Okay, so they are using the space shuttle main engines, also called RS-25 engines. They have quite a few of them, left after the grounding in the space shuttle. So they're going to use those up. 4 of these engines for the main part of the vehicle, and then a interim cryogenic stage. But they have all tested the J2 They actually rebuilt the J2X. They took the blueprints, improved it, the turbo pump, the nozzle, etc. So J2X has been tested, works beautifully, okay? But it's on the shelf somewhere. So they're going to use that later. This one. This has a capacity of 130 metric tons. It's as much as the Saturn V, initial version. The final version, Apollo 15, 16, 17, was 140 metric tons. So that is capable of building international lunar village if we decide to. Okay. If you become a AWA member, you get a monthly magazine. How many of you get it? Okay. Did you see the recent one? Take a look at it. There's an article by somebody advocating going back to the moon before going to Mars. Okay. So anyway, if you are seriously interested in this business, if you seriously want to become a rocket scientist or a rocket engineer, you need to, become an AWA member and so on and so forth. Okay. Anyway, RS-25, beautiful engine. Okay. Very high performance engine, 452 seconds vacuum. Okay. It uses what is known as staged combustion. I won't go into it now. I'll come back to that. It's a very good design. Works beautifully. Almost gold-plated, so to say. I mean, it's we build expensive, high-performance things. Unlike the Russian philosophy, they build just enough, not the best and the greatest. Okay. Okay. Comparing the Falcon 9 with the SLS, simple serial stage. I'm showing only the Falcon 9. This is cut out to show the internal configuration. Look at the first stage engines and the vacuum engine. The difference is, of course, a longer, higher expansion ratio nozzle. That's all. Everything else is the same. So that is one way to reduce the cost. Okay, instead of building a custom-built engine for the upper stage, why not use the first stage engine, right? That was a Chinese philosophy. They built a single engine and then cluster of those for the second stage and so on. Cheaper. Serial staged. Of course, Falcon 9 Heavy is going to be parallel staged. And in that case, you know what they do? They essentially cross-feed the propellants into the boosters so that the boosters can be expanded early and the main engine can still go. So that cross-feeding of propellants is once again an important step they have to make sure works. Moderate thrust engine. Look at the specific impulse, rather low compared to a very good cryogenic engine. But there are advantages to using RP1 because the mass of the system comes down, because it's a high-density propellant compared to low-density liquid hydrogen. So that is one of the differences. This is a simple gas generator cycle in which the gases used to drive the turbo pumps are just exhausted, whereas in the space shuttle, those gases are not wasted. They're injected into the main thrust chamber. That is why its performance is higher. Aluminum lithium. Why should we use aluminum lithium? What is the advantage of aluminum lithium? It's being used everywhere, aircraft and so on.
Strong, light, and readily available.
Stronger and lighter. 10% lighter and 10% stronger, something like that. I used to remember these numbers, but getting old, can't remember every one of those numbers. The main problem is this is not human rated. It is one thing to build a launch vehicle to launch cargo, another thing to build a launch vehicle to launch human beings. High degree of redundancy has to be built in, and you have to make sure a single failure or double failure cannot compromise the mission. So that It requires a lot of work. So once SpaceX got back into the launch business, it remains to be seen whether they can convince NASA that their vehicle is safe enough to carry our astronauts to the International Space Station. Okay. Now, they are not doing themselves any favor by saying we are going to have the astronauts on top of the vehicle while the vehicle is being filled. NASA has just come out and said, no way, you can't do that. That is compromise the safety of the astronauts. Why would they want to do something like that?
They use the super-cooled liquid oxygen that can only be kept in the rocket for so long before it expands and has to be redone.
Yeah, the fill time is less than 45 minutes. So you had to have the vehicle filled with propellant in about 45 minutes and launch. Now, if it takes another hour for these astronauts to get in and make themselves comfortable, the advantage of super cooled propellants is gone. So
the president of SpaceX has come out saying several times, though, that their philosophy is that they'd rather have the crew like inside the capsule, which has a launch escape system, while it's fueling, because rather than approaching the rocket while it's sitting there.
The latter one has been tested by NASA and works. This one we don't know. I would be very uncomfortable sitting on top of something that's being fueled. Yeah, just anyway. We will see. We will see what happens. Okay, I mean, we will see. Now, look at the size of this landing legs. I mean, it's amazing. Hydraulically actuated landing legs. Just prior to landing, they're deployed and so on. They added a significant inert mass to the first stage, but did not compromise the performance too much. And interesting, the technology. This ship. Elon Musk is, famous for giving it all sorts of, silly names. But anyway, what is it? Just read the manual or something like that.
One on the West Coast.
Yeah. But anyway, technology used is the one that drilling ships use. Okay. Now, if you're drilling in several mile deep waters, you have to position your drilling ship accurately within whatever meters or something like that. And they use thrusters, and using GPS positioning system, they position it carefully. Same thing is used to maintain the position. Obviously, in very high sea states, maintaining position could be difficult. Okay, but if you are going to recover the first stage, it is better to recover it down, over the ocean near the coast, rather than try to bring it back, because that requires more fuel, obviously. So you can't do that. Whereas the ULA system, you just have to have a helicopter ready and make sure the catch mechanism works, of course. But you can catch it anywhere, okay, and bring it back. Okay. I don't know why they did not think of this before. The original configuration was this. The new configuration is this. They call it OctaWeb. Why wouldn't you have thought of this a priori? Okay. Now, this transmits the loads, structural, the forces to the structure much better, and therefore the mass, inert mass comes down. Okay. The OctaWeb. This is how it looks. Just look at the size of these things. They are, how many of you have seen the Saturn V vehicle in the Kennedy Space Center? If you ever have a chance, go and see that. Yeah, it's a humongous. It's awe-inspiring. It's to think that we built all that in a matter of a few years, 5 years or so, and worked, beautifully. It's amazing to me, anyway. Okay. The main nozzle, the thrust chamber, the nozzle, and this is the turbopump exhaust. In other words, this is a gas generator cycle in which this exhaust is not injected into the main engine. Okay. Now, when you generate the hot gases to drive the turbopump, there is what is known as a gas generator. Okay. Now, the gases generated drive a turbine, just like in an aircraft engine. The hot gases drive the turbine, that drives the turbopump, right? Now, in order to keep the design simple, you have to limit the temperature, of the gases generated to about 1,000 degrees Kelvin or so. Okay, so that usually requires either rich or lean combustion. In this case, rich combustion, so you can see the gases coming out. Rich combustion usually, means incomplete combustion, and you can see the black plume coming out compared to the good combustion in the main nozzle coming out. So, thrust weight ratio of 155, higher than 137 of NK33. Yeah, really nice. This one, I don't know whether it
Liquid oxygen tank.
Okay, let's show you this. What I wanted to show you was how the propellant looks in zero gravity. Okay. Oh, I didn't. What the heck happened here? Where is it? Was it this? Was it 53? I forget. I don't want to go through the whole thing, but I will, put it on the web on D2L so you can watch. Okay. The reason I'm showing you that is you have to make sure that the intake of the pump always has liquid propellant. Okay, so you have to have a certain G forces acting. So when the engine is thrusting, there's not a problem. The propellant is forced towards the outlet area. But when the engine stops thrusting in microgravity, you see that the propellant essentially, becomes, huge droplets. So where is that? Oh, yeah, I think it's early in the beginning. See what the propellant looks like when the engine has stopped thrusting? You can't have that, right? Anyway, it is usual to provide a slight amount of thrust by whatever means in space so that you have some gravity acting on the propellant so that you can feed liquid propellant into the engine for space engines. Okay, the Orion capsule. This is our Apollo capsule on an asteroid, on steroids. This is supposed to take our astronauts to asteroids and so on and so forth, Mars and so on. But this was a leftover from the Bush program, Constellation program. I think Lockheed Martin is the builder. So this heat shield is a lightweight, well-proven heat shield. It was actually tested about a year ago, something like that. And it was recovered successfully. So we have the capsule. We still don't have the launch vehicle. Okay. How many of you are anxious to leave? Can I take a few more minutes?
I need to go.
With your permission? Okay. Atlas V, the workhorse. 5 boosters in this case, RD-180 engine at thrust of 3.8 million newtons. Very powerful engine. Okay. Compared to that, Merlin is 0.6 meganewtons. Did I say millinewtons? Meganewtons. Meganewtons. Okay. Millinewtons only for space propulsion. First stage. See the various components. I wanted to show you this. What it takes to connect different stages, and all these masses are important. Okay. In computing the performance. And this is, of course, the Centaur upper stage, which is essentially RL-10A version of the engine, the Pratt & Whitney engine, and of course the fairing that encloses not only the upper stage but also the payload. Okay, this is what RD-180. RD means Rocket Naya Dvigatel, means essentially rocket engine in Russian. Okay, let me stop here. You guys are anxious to go. All right. See you on Thursday.